Rudra, students is not here, his paper on getting fluorine excited states using TDDFT was with me. So what I'm going to do is motivate that this can really give, right? Now, the first thing I'm going to do is extension of Thomas Fermi theory by block for time dependent potentials. Now remember, I will not write Thomas Fermi, we will take it in the end. In stationary state theory, I have an energy function, E rho, right? Rho is time independent. Now if I have a time dependent potential, then I'm going to have rho r, which will depend on time, right? Now, what we are going to do is, essentially what you have seen is that working in terms of density implies treating electron gas as a fluid. So I'm not talking about Kohn-Sham formalism right now, I'm talking about really working in terms of density, then it is treating like a fluid. So what we are going to do is, if I have a time dependent potential and time dependent density, first thing that is satisfied is d rho dt is minus del dot J, where J is the current. J is some velocity times rho. That's the continuity equation that will always be satisfied. Right? So, necessarily I have a current also. I remember yesterday when we were doing Runge-Gross theorem, I had to bring in some current, JRT, that's what we used. So, there is a current, and what Bloch says, and makes an approximation, that this V can be written as grad of some function. That means, what is the approximation? That V does not have a curl. This curl vanishes, right? That is the approximation. There is no just in rotation. And then you write the energy or a functional. Let's write a functional which I will then identify the energy for periodic potential. Let's write a functional E rho, which will be the kinetic energy of the fluid, which will be grad phi square V, where V could be time dependent, could be time independent, but nonetheless is there, right? Oh, grad phi square is already V square times rho plus E rho. I'm just writing the functional, let's write as TD. Now, ETD has meaning of energy for periodic in time potentials. And then what you do is you take E TD equals time average of 1/2 integration grad rho grad phi square rho plus E. Okay, then it has the meaning of quasi-energy that we introduced yesterday in flow K theory. Otherwise, there is a functional there, ETT, some function. Alright? Now, what I'm going to show you is, now I want to get the equation. For phi and rho. How do we get that? Right? This is time dependent, so I don't know how to minimize it. The only thing I can minimize is this, but in general, I don't know how to minimize it. So what I'm going to show you is that phi and rho are canonical variables in the sense of Hamilton principle. Okay? So how do we show that? Well, the equations will give me that indication, and then I'll take that to be the indication that phi and rho are canonical variables, and then I'll write the equation for the other. So if I take delta ETD delta phi, after all now there are two functions, phi and rho, right? And you know what to do in that case. In that case, all you're going to get here is term from here itself. And what will that be? That will be divergence of grad rho grad phi. This you can check, because what is this functional derivative? This is nothing but d, that inside integrand d phi minus grad of d by d grad phi of the integrand. So give you this minus sign. Alright? And this is nothing but minus divergence of j. Remember j is this. We took v to be this, therefore, right here, with this, you get j equals grad phi times rho. And this is nothing but minus plus d rho dt. And that's Hamilton's equation. One variable, right, rho, this time derivative is equal to the derivative with respect to the other variable. Right? And therefore, I'm going to have d phi dt equals minus delta u delta rho. That's the other equation. So then I'll know both phi and rho change, and I can solve my equation. So what do I get? If I do that, I get d phi dt. I'll put the minus sign on the other side so that I write again and again. I take d by d rho will be equal to 1/2 grad phi square plus delta e rho delta rho. All this was done in the context of Thomas Fermi theory. Okay, so finally I'm going to take E as a Thomas Fermi function. By the way, when I wrote this, right, this was equivalent to flow K theory, time average of psi Great job.